the film number 5 and the final film is about integrators and derivators. And we have already seen at other applications like amplify, which is basically to multiply with a constant. Instrumentation amplifiers are used for subtraction, or to take the difference between two signals. Filters are used to take away and keep frequencies in a signal. And we also have something called summing amplifiers, which is covered by one of the tasks associated with this lecture. And finally, integrators and derivators. So the name operational amplifiers comes basically from all the different operations that you can perform when you have operational amplifier. The filters are also based on the inverting amplifier, but we replace R1 or in some cases R2 with a capacitor alone, not a combination of resistor and capacitor like we had in the filters. So let's first look at the integrator. With the integrator, we replace the R2 with a capacitor. Since we only have one resistor and one capacitor, we don't need to have subscript, so we simply call this R and this one C. There is no current going through here, because that's the property of the basic operational amplifier. So the current here is V in over R. The current has to go up there, and the current in a capacitor is defined by its integral. The voltage across is defined by the integral 1 over C multiplied by the integral of the current. So the V out is the opposite of, say, V out is plus minus here, or if you like plus minus here, which is the opposite sign of the capacitor voltage. So the V out, the opposite sign of the capacitor voltage, is 1 over RC and the integral of the voltage V in. Why integral of voltage? Well, that is because the current is a function of V in. So, and R is constant, so R can go, it should really say over R here, but the R can go on the outside of an integral because it's constant, and you end up with having V in here. So it's the integral of your input voltage. Hence, the integrator. The derivator, remember the integrator had a capacitor here, the derivator has the capacitor here, and the current through the capacitor is C dV over dt. And the capacitor voltage is the same as the input voltage, so therefore it's C multiplied by dVi over dt. That's the current. And the same current goes up here, and the voltage across the resistor is the current multiplied by the resistor. So you have the current multiplied by the resistor, and the resistor multiplied by the current that we found here. V out is measured from here to here, which is the opposite of, or it's the same that we measure from here to here, which has the opposite sign compared to the resistor voltage. So therefore, opposite sign, and the resistor voltage there, which we found here. So the output voltage is now a derivation of the input voltage multiplied by some constant. So that RC will form the gain associated with this derivator. This also, of course, is an important part of a PID controller, where you have integrator and derivator, and the proportional part, P, is formed by a standard inverting amplifier with resistors only. Like that. So that's the P part. Here's the I part. And here's the D part, which will form a PID controller.